Mathematics, paper number MTH 402A and 402B. Title for 402A is Differential Equations, and for MTH 402B title is Differential Equations and Numerical Methods. First chapter, Theory of Ordinary Differential Equations. So, what is an ordinary differential equation? First of all, we require dependent variable and independent variable. So when we write dy by dx, y is called dependent variable and x is called independent variable. Variable in the denominator is independent variable. So an ordinary differential equation is a differential equation in which number of independent variable is one, only one, and number of dependent variable is one or more than one. So any differential equation containing one independent variable and one or more dependent variables is called ordinary differential equation. For example, dy by dx plus xy equal to e raised to x. Here it contains one independent variable x and one dependent variable. So it is ordinary differential equation. Now second example, d2y by dx square plus dz upon dx plus 2yz equal to e raised to y into z. So again, we have one independent variable x and more than one dependent variable y and z. So this is an ordinary differential equation. Now next we define Lipschitz condition. So we say that function fxy satisfies Lipschitz condition in a region D of xy plane if there exists a positive constant k such that this difference f of x comma y2 minus f of x comma y1 modulus, that means positive value of this difference, is less than or equal to this constant k times mod of y2 minus y1 for all points x comma y2 x comma y1 in the region D. So if this is your region D and suppose this is a line y equal to y2, so these are the points with y coordinate y2 x comma y2, and suppose there is another line y equal to y1. So all points on this line will have coordinates x comma y1. So there are infinite number of points on the line. So if the values of the difference of values of the function at f of x comma y2 at all these points minus value of the function at all these points, if this difference is less than or equal to constant time y2 minus y1, constant time y2 minus y1, and this hold for all points x comma y2 x comma y1 in D. So x comma y2 x comma y1 can be any point in this region D. So when the difference f of x comma y2 minus f of x comma y1, this difference is less than or equal to k times y2 minus y1 for all points x comma y2, x comma y1 in the region D, then we say that function satisfies Lipschitz condition in this region D, and k is called Lipschitz constant. Now, if fxy satisfies this condition, new condition, partial derivative of f with respect to y is smaller than k for all points xy in the region D. Which condition hold? Partial derivative of f with respect to y, this value of this partial derivative is smaller than k for all points xy in the region D. Then for the same constant k, Lipschitz condition also satisfies. Let us see how. Now, from equation 1, this is a Lipschitz condition, f of x comma y2 minus f of x comma y1, its modulus less than or equal to k into y2 minus y1. So from this equation, we take this term mod of y2 minus y1 to the left hand side, or divide both sides by this term mod of y2 minus y1. So we get f of x comma y2 minus f of x comma y1, and this term mod of y2 minus y1 we have taken from right hand side to left hand side in the modulus. Now, by Lagrange's mean value theorem, applying to this function f with respect to y coordinate. So if we apply, instead of f of x, if your function is a function of y, and if we apply Lagrange's mean value theorem to this function y on the interval y1 minus y2, we get f of y2 minus f of y1 upon y2 minus y1. So here, suppose x is fixed and apply Lagrange's mean value theorem with respect to variable y. So what we get? F of x y2 minus f of x y1 upon y2 minus y1. This is equal to, what is the Lagrange's mean value theorem? Partial derivative of the function with respect to y at some point in this interval y1 y2, open interval y1 y2. So here we get partial derivative of f with respect to y at the point, say y bar. Y bar is a point in the interval y1 y2. So that means by Lagrange's mean value theorem, this expression is nothing but partial derivative of f with respect to y at some point y bar, where y bar is some value in the open interval y1 y2. So we find that when partial derivative of f with respect to y is less than k, partial derivative of f with respect to y is less than k, in that case, this expression is the same as this Lipschitz condition. F of x comma y2 minus f of x comma y1 is less than or equal to k into, take this y2 minus y1 on the right hand side, so it is Lipschitz condition. For the same constant k, Lipschitz condition also satisfies. So if partial derivative of the function f, which is a function of two variable, with respect to y is smaller than k, then for the same constant k, Lipschitz condition also satisfies. That is, Lipschitz constant will be same, which we get in this equation, that mod of partial derivative of f with respect to y less than or equal to some constant k. So same constant k can be used in the Lipschitz condition. Now let us solve some examples on Lipschitz condition. Show that the function, which is a function of two variables, x into y square, satisfies Lipschitz condition on the rectangle, but does not satisfy Lipschitz condition on the strip. Now, why it is a rectangle? Mod x less than 1 means x lies between -1 and +1, and mod y less than 1 means y also lies between -1 and +1. So suppose this is x axis -1 and +1. So x lies between -1 and +1. And suppose this is y equal to 1. This value on the y-axis is y equal to 1, and this value on the y-axis is -1. So y lies between +1 and -1, from -1 to +1, and x lies between -1 and +1. So we get this rectangle. In this rectangle, from x equal to -1 to x equal to +1, and y equal to -1 to y equal to 1. This is y equal to 1. This is y equal to -1. So this is a, what we say, it is a rectangle. On this rectangle, show that Lipschitz condition satisfies. And what is a strip? Mod x less than 1, that is same, -1 less than x less than 1, same region. This is -1, this is +1. This line is x equal to -1. This is x equal to +1. This is y-axis, which is x equal to 0. And what is y? Y is less than infinity. Mod y less than infinity means what? Y lies between -infinity and +infinity. So y can take any value. So up to infinity, up to -infinity. So what is a region? Up to infinity, up to -infinity. So anywhere. So this is a strip in between x equal to -1 and +1. So y is not finite. Y can be any value, minus infinity and y or plus infinity. Y can take any value in between minus infinity and plus infinity. So it is a strip in between minus x equal to minus 1 and x equal to plus 1. So one region is a rectangle and another is a strip. So this strip is this region. This is y-axis, this is x-axis. This value is here, x equal to 1. This value is x equal to minus 1 on x-axis, and this value is plus 1 on y-axis, and this is minus 1 on y-axis. Whereas this strip means if this is y, this is x-axis, again x lies between minus 1 and plus 1, and what is y? This is minus 1 to plus 1. This is a range for x. But what is the range for y? Mod of y less than infinity. So that means y can be anything, any value up to plus infinity, up to minus infinity. So what in between x equal to minus 1 and 1. So this is a strip. This is a strip. This is of length, of infinite length, right? Of infinite length in between plus 1 and minus 1. So show that function satisfies Lipschitz condition on the rectangle but does not satisfy Lipschitz condition on the strip. So given function is f of xy equal to xy square, x into y square, and the region is a rectangle, mod x less than 1, mod y less than 1. So we use this technique, find out partial derivative with respect to y. So it is 2y, x into 2y. So 2xy. What is modulus of this partial derivative with respect to y? It is modulus of 2xy. 2 is constant, so mod x into mod y, because mod of a into b is mod of a into mod of b. So we can separate this product. But in the given region, this value is less than 1, mod y is also less than 1, mod x is less than 1. So less than or equal to 1 into 1. So this product is 2. So this partial derivative is less than 2 for all xy in the region D, where mod x is less than 1, mod y is less than 1. So when partial derivative of f with respect to y is less than k, then for the same constant k, Lipschitz condition satisfied. So function satisfies Lipschitz condition with Lipschitz constant k equal to 2. Same constant can be used in Lipschitz condition. Now next consider the region, same mod x less than 1, but now y can be any value in between minus infinity and plus infinity. So again, what is partial derivative of f with respect to y? It is 2xy. So modulus of this partial derivative is mod of 2xy. That is 2 is constant. So it is mod x into mod y. Now mod x is less than 1, but y can be any value in between This is a second region. We are taking second region. It is a strip mod x less than 1, mod y less than infinity. So since y can be any value up to infinity, so when y tend to infinity, this product will tend to infinity. So that means value of this derivative tends to infinity. So that means the constant k does not exist, because this is the actually the expression for this derivative represent the expression of Lipschitz condition. So that means when constant k does not exist, so that mod of this derivative is less than or equal to k, Lipschitz constant does not exist, because value of this derivative tends to infinity. So there is no constant k for which this derivative is smaller than k for all points xy in the region D. So k does not exist. So Lipschitz condition does not satisfy. Now, or can we use a definition of Lipschitz condition? So let us use definition and show that same problem satisfies the definition of Lipschitz condition. So to show if xy satisfies Lipschitz condition on the rectangle, first region is a rectangle mod x less than 1, that is x is in between -1 and +1, y is also in between -1 and +1. Show that function satisfies Lipschitz condition means f of x comma y2 minus x f of x comma y1. This difference, its modulus, is less than k into mod of y2 minus y1 for all points x y1 x comma y1 x comma y2 in the region D. D is mod x less than 1 and mod y less than 1. So function is xy square. What is the this value f of x comma y2? Put y equal to y2, we get x y2 square. Put y equal to y1, we get x y1 square. So the difference f of x comma y2 minus f of x comma y1 is x y2 square, x y1 square, x is common, y2 square minus y1 square, factors y2 minus y1, y2 plus y1. So this difference f of x comma y2, x comma y1 is equal to x into y1 plus y2 into y2 minus y1, y2 plus y1 into y2 minus y1. Now take modulus mod of f of x comma y2 minus f of x comma y1 is equal to modulus of right hand side. Right hand side contain x, y2 plus y1, and this difference y2 minus y1. The mod of a into b can be separated as mod of a into mod of b. So it is equal to mod x mod of y2 plus y1 and mod of y2 minus y1. But mod x is less than 1, mod of y is less than 1 when in the region D, value of y is less than 1. y2 and y1 are any two value in D. But mod of a plus b is smaller than mod a plus mod b. Right? So this is smaller than mod of y2 plus mod of y1. Right? And every value of y is less than 1, every in D. So mod of y2 is less than 1. Mod of y1 is also less than 1. 1 plus 1, 2. So from equation 1, this is your equation 1. Mod x is less than 1. This is your equation 1. Mod x y1 plus mod of y1 plus y2, and this different. So mod x is less than 1 in the region D. Mod x is less than 1. Mod of y1 plus y2 is smaller than 2. and y2 minus y1, this difference as it is. So we get 2 into mod of y2 minus y1. So f of x comma y2 minus f of x comma y1 is smaller than k into mod of y2 minus y1, where k is 2, and this hold for all points x y2 x y1 in the region D. So Lipschitz condition satisfies on the region D with Lipschitz constant k is equal to 2. This is the value of k. So same problem can be solved using definition, that is the same function satisfies Lipschitz condition if we use the definition also. Now there is a second part. There is another region where it does not satisfy Lipschitz condition. So let us see the second part. Next, to show this function, same function x into y square, does not satisfy Lipschitz condition on the region D, given by first condition is same, first condition mod x less than 1 for the region D, but second is different. Y can be any value in between minus infinity and plus infinity. Now again, we have to show that if this inequality satisfies, then Lipschitz condition hold, and when it does not satisfies, then Lipschitz condition does not hold. So function is again same. Find out x comma f of x comma y2, f of x comma y1, their difference x y2 square minus x y1 square, x is common. Same, a square minus b square is a plus b, a minus b, so it is y1 plus y2 into, sorry, y2 plus y1 minus y2 plus y1 into y2 minus y1. This is a factor. These are the factors for y2 square minus y1 square. Take modulus. So we get x into mod of f of x comma y2 minus f of x comma y1 is equal to modulus of right hand side contains three terms, mod x, mod of y2 plus y1, mod of y2 minus y1. Now put y1 equal to 0, because the range for y is now from minus infinity to plus infinity. It also contains this value y equal to 0. So take some value of y, which is y1 as 0. y1 is some value of y. So let us take y1 equal to 0. That is, consider this point x comma y1 is now, put y1 equal to 0, we get x0. So this is x0, right? So this is, we are substituting the value of y1. On the right hand side, it is mod x, y1 is 0, so we get mod y2. Here y1 is 0, we get mod y2. So y2 square, right? So mod of x into y2 square. y2 is again some value of y, and y can take any value in between minus infinity and plus infinity. So when y2 tends to infinity, as y2 tends to infinity, y2 square also tends to infinity. So mod of y2 square tends to infinity. So this difference tends to infinity. That is, this value tends to infinity. So k does not exist. We want this difference less than or equal to k if it satisfies Lipschitz constant, sorry, Lipschitz condition. Then this difference we want less than we want this difference less than or equal to k into y2 minus y1 like this, but here it does not exist. It tends to infinity when y tends to infinity in this case. So the constant k does not exist because this difference tends to infinity as y equal to y2 tends to infinity. So k does not exist such that this difference is less than k into mod of y2 minus y1 for all x comma y2 x comma y1 belongs into the region D. Here region D is mod x less than 1 and mod y less than infinity. Now in this region mod y less than infinity we have consider which point? We have considered x comma y1 as x comma 0 here. This is a case. And for these points, Lipschitz condition does not hold. So it will not hold for all points in the given region D. So that means K does not exist which satisfies Lipschitz condition because K does not hold, K does not exist for the points x comma y1 where y1 is 0. For such points, Lipschitz constant does not exist. So that means for all points in the region D, Lipschitz condition does not hold. So Lipschitz condition does not hold for this strip. So we are using a definition of Lipschitz condition here. So for this region, the Lipschitz condition does not hold. Using the definition of Lipschitz condition, we have solved this same example. Second problem, if S is defined by the rectangle mod x less than a, mod y less than b, show that function fxy, which is x square plus y square, satisfies Lipschitz condition on the region S, where S is given by this rectangle mod x less than a, mod y less than b. So instead of 1, now the values are a and b. Right? Mod x less than a means x lies between plus a minus a. Mod y less than b means y lies between minus b and plus b. So given function is f of xy equal to x square plus y square. Given region is mod x less than a, mod y less than b. Find out partial derivative with respect to y. It is twice y. Take its modulus. So it is mod of 2y. 2 is positive, so it is 2 into mod y. And mod y is less than b. So we get twice b. So this partial derivative, its modulus is less than twice b for all points x, y in this region. This is a region S. For all points x, y in the region S. So when this partial derivative with respect to y, its modulus is less than k, same constant can be used in the Lipschitz condition. So function satisfies Lipschitz condition with Lipschitz constant. What is the Lipschitz constant? K equal to twice b on the given region mod x less than a and mod y less than b. This is a region S, given region. So this function satisfies Lipschitz condition. What is the Lipschitz constant? Twice b is the Lipschitz constant. Next example, if S is defined by the rectangle mod x less than or equal to a, mod y less than or equal to b. Show that the function fxy equal to x into sin y, y into cos x plus y into cos x satisfies Lipschitz condition on this rectangle S. So given function is x sin y plus y cos x, and given region is mod x less than or equal to a, mod y less than or equal to b. Find out partial derivative with respect to y. So partial derivative of f with respect to y, x is constant. Then derivative of sin y with respect to y is cos y, plus derivative of y is 1, cos x is constant as it is. We are differentiating with respect to y. With respect to y, x is constant. So derivative of sin y is cos y and derivative of y is 1. X as it is, cos x as it is. Take modulus. So mod of x into cos y plus cos x. Now again, mod of a plus b is less than mod a plus mod b. Separate the two terms. And mod of a into b is less than mod a into mod b. So again, separate this product. Mod x into mod cos y plus cos x. Now, any value of cos x is less than 1. So this is less than or equal to, and mod of cos y is less than 1. Mod of cos x is also less than 1. And in the given region, what is the given region? Rectangle, mod where mod x is less than or equal to a, mod y is less than or equal to a. So this mod x is less than or equal to a. So a plus 1. What is the Lipschitz constant? A plus 1. So mod x is less than or equal to a, and cosine is less than or equal to 1. So mod a into 1 plus 1. So this value is larger. Cos y is smaller than 1. Cos x is also, mod of cos x is also less than 1. So we get a plus 1. So partial derivative of a with respect to y is smaller than constant k, where k is a plus 1. So therefore, a function satisfies Lipschitz condition on the given region with the Lipschitz constant k equal to a plus 1. This is a constant k equal to a plus 1. With this Lipschitz constant, Lipschitz condition satisfies by the function f of x comma y. Now next example. By an example, show that a continuous function may not satisfy Lipschitz condition. So every continuous function may not satisfy Lipschitz condition. For example, f of xy equal to y raised to 1 upon 3, and D is the region mod x less than or equal to 1, or mod x less than 1 and mod y less than 1. Mod x less than 1, mod y less than 1. So find out partial derivative. It is a continuous function. Y raised to 1 upon 3 is continuous because y is continuous. So its power 1 upon 3 is also a continuous function. Find out partial derivative with respect to y. So it is 1 upon 3, y raised to 1 upon 3 minus 1. 1 upon 3 minus 1 is minus 2 by 3. So it is 1 upon 3 into 1 upon y raised to 2 by 3. What is the modulus? Modulus is 1 upon 3. This is positive number. 1 upon y raised to 2 by 3. Now this tends to infinity if y tends to 0. If y tends to 0, 1 upon y, that is 1 upon 0 is infinity, that is 1 upon y will tend to infinity. So when y tends to 0, 1 upon y raised to 2 by 3 tends to infinity. So that means Lipschitz constant k does not exist, its value is increasing indefinitely. So Lipschitz constant does not exist over this region D. So function does not satisfy Lipschitz condition, though it is a continuous function. So function does not satisfy Lipschitz condition on D, on this region D, but it is a continuous function. Y is a continuous function, so y raised to 1 upon 3 is a continuous function. So thus function is continuous, but it does not satisfy Lipschitz condition. This is a homework. Check whether this function y raised to 3 by 4 defined on the rectangle satisfies Lipschitz condition or not. Try to solve this example. Function is y raised to 3 by 4.